morning. This is your first class of Nano Electronics, and I am Krishanu Mitra, Assistant Professor SIA. Uh, so it's a kind of new subject in your curriculum, like Nano Electronics. So here in Nano Electronics today we'll discuss about the curriculum, what we are going to discuss, what are the things you need to be focused on, and actually this topic is quite vast. Okay, which include nanotechnology also, applications of nanotechnology or nanoelectronics in medical applications. So this kind of things we need to discuss in this curriculum. We'll start with the introduction of nanotechnology when we are going to start the curriculum. At the very beginning, we need to understand what is nanotechnology. Okay, till now whatever we have studied in electronics, all these things are in micro scale. Okay, and that is in 10 to the power 6 range. Okay, and then when we are going to nano scale, it's 10 to the power minus 9. Okay, so things are becoming so small so that you cannot realize. Okay, and for that thing you need to be very understandable about the quantum mechanics also. Okay, and for that we'll discuss so many topics related to quantum mechanics, like mesostructure, basics of quantum mechanics, then Schrodinger equations, density of states, particle in box concept, which are very important, divergency, band theories of solids, all these things we need to discuss. Okay, among whatever topic I have told, among them, the most important topic will be the Schrodinger equation, which is a very important thing you should know for quantum mechanics and has a wide application in nanoelectronics also. Okay, so then we will discuss about the particle in box concept, whatever I have told. It's a kind of conceptual thing. You cannot relate it directly with the physical particles or physical things, whatever we see in our real life. So many things you need to be visualized for understand this kind of topics. So, in particle in box concept, what happens that if we consider, I will go in detail on with all the topics. Okay, but as it is introductory class, so I'll give a very basic idea. Okay, on that on few topics. Okay, so that you can get to understand that what is the subject matter we are dealing with. Okay, and in future also what will be the subject matter we will be dealing. So, in particular box concept, we need to consider a box. Okay, and if there is an electron inside the box, a single electron, we made a vacuum box. Okay, and say suppose a single electron is present on that particular box, inside this particular box, then if you ask to find some parameters on that particular electron, a parameter means its position, weight, acceleration, on all other things. Then you will find that you cannot determine a particular position for a particular electron on that particular box. Okay, if you do some experiments related to this thing to find out the position of that electron, you will find that at the same moment you will find it something, say suppose this is a box, this is the area of the box, you will find that electron here for a particular experiment, and then at the same time you are doing another experiment to find the electron on that particular box, you will find that electron at the same time is present over here. Okay, so this is a kind of contradictory thing that for a particular moment of or particular instance of time, this electron are present in the both the places. Okay, it should be present in a particular place, and then after some time it can move to another place. But in this concept of particle in box concept, you'll find that this electron will be present here, and at the same time it will be present over here. Okay, which is not possible in physical world. So that's why I've told you that you need to be you need to be a little bit of you need to pay your attention to understand these concepts. Okay, and uh, there is a factor of probability also that if I ask that if you done the experiment and you'll got some properties of that electron, and then I ask that where the electron should be now, then you cannot say a particular place that here the electron should be lying. There will be a probability factor. Okay, you can say that a 5% probability is there to present the electron in this position, and then you can say that 10% probability is there to present the electron for another particular place. So this kind of contradictory concept will be there, which we need to deal. Okay, so this is a particle in box concept. Very basic thing I have discussed. There are lots of things that there we need to discuss. We will discuss in detail in the classes. Then we need to understand the band theory of solid. Okay, so what is band theory? Band theory, we all know what is band theory actually. We have studied in the, from the first year in basic electronics. Then we have studied this band theory in solid state device and as well as in analog electronics also. So I'm not going in detail on the band theory because it's a kind of easy topic and we'll discuss in detail in class. And then we need to understand the CMOS scaling. Okay, after completing this portion, that is the quantum mechanics portion, the basics of quantum mechanics portion and basic of nanotechnology portion, will enter to our real life practical problem related issues about FET and MOSFETs, which are the most widely used semiconductor device in today's world, which are used to develop the ICs. Okay, ICs, we all know what is IC. IC means a semiconductor chip which can perform several type of activities, and we can define that. You know what I am talking about. So my mobile, my laptop, everything consists of thousands of transistors, and these transistors are nothing but a MOSFET. Okay, so you have seen that the initial level when the mobile was invented or mobile was just came into the market, we have start purchasing it. That mobile has a very minimum number of operations. Like with the mobile, we can call it this mobile. We can we use this mobile to talk to each other. Okay, we can send the message. That's it. This is the basic purpose of the initial mobile technology. Then the revolution came and we got the smartphone, and by which we can do several types of activities like we can browse web, we can communicate through WhatsApp, we can do Facebook, and so many others things are there. There are calculator, calendars, there are thousands of apps are there for several kind of applications. Okay, so all these things are happening because of this MOSFET. Okay, the more number of MOSFET we can integrate in a particular chip, the more functionality we can achieve from that particular chip. Okay, so to embed more number of MOSFET in a particular chip, we need to scale down the MOSFET. Okay, initially when the transistor was invented, the MOSFET is a nothing but a transistor. So when the transistor was invented, and its size was quite big. When it was first fabricated, size was like something like this, a single MOSFET. Okay, so if a single MOSFET is taking that amount of space, then I have told that this mobile has lakhs of transistors, lakhs. So you can imagine, if we are living in 50th centuries, like 1950, 1947, when the transistor was invented, if we are living on the till 1947 century, then if we want to a mobile, this kind of mobile which has a operation like same as this mobile, then how much space we require? It will consist our overall building. Okay, to perform an operation which can perform an operation which is done by this mobile. If we want to perform the same operation with the initial level transistors, then we can then we have to have the space of around this whole building, because the size of transistor is this much. But nowadays the size of the transistor is in nano meter, okay, which is very small, very small. Okay, so what happened, so more number of transistor we can embed in a particular chip, the more the chip became more functional. Okay, so for I'm taking an example, like a calculator is there which has a chip inside it, and now we need to perform now we need to embed the calendar. Okay, we need the functionality of calendar also with this same calculator. Then what we need to do, we need to add another chip to that calculator so that it can display the date and time. So we need to add a chip. That means we need to add some MOSFETs. Then we say, suppose we need a more number of operations, like we can call with this with that device, with that calculator. So what we need to do, we need to assemble so many other chips with the calculator so that you can call with the calculator. It can show the mobile number. It can communicate with the it can communicate to the tower. So what we found, that more number of transistors we can embed in a particular chip, the device became more functional. And for that reason, we started scaling down the MOSFET. That how we can develop a MOSFET whose size is so small. Okay. So when the size of that MOSFET became so small, it may have some consequences. So initial level, we didn't face any kind of consequences when we are trying to scale down the device, and the Moore's law are obeying as usual. We know what is Moore's law is. Moore's is a very renowned scientist and an entrepreneur who have founded Intel Corporation. He published a paper and told that every year the number of MOSFET which can be embedded in a particular chip will be increased rapidly. There is a curve is there. I will also discuss on that thing also, that topic. So, but nowadays we have reached a certain level where the Moore's law is not obeying that particular rule. And why it's happened? Because of MOSFET scaling. Scaling means when we try to shrink down the size of the MOSFET, there are so many other factors are there which became the obstacle to scale down the MOSFET. This obstacle is called scaling factors. There are so many factors when we try to scale down the MOSFET. There are so many factors included here. And when we try to scale down, where we need to work, basically we need to work on the uh, uh, channel length. particular each and every MOSFET has its channel. Okay, and depending on this channel, we can divide the MOSFET into two types. One is enhancement type MOSFET, one is depletion type MOSFET, as you all know. So depending on this channel, MOSFET can be divided into two parts. And when we are trying to shrink down the size of that MOSFET, we need to shrink down the size of the channel. Okay, so when we shrink down the size of the channel, there is a ratio which is W, which we called as W by L ratio, and W means the width, and L means length of that particular channel. So when we vary the W by L ratio for a MOSFET, at the initial level, it's okay, but when it came to a nanoscale, it's not functional. It not functions properly for that particular MOSFET. And to understand this, what's going on here, you need to understand the scaling factors. That what are the factors are there when appears when we are trying to scale down the size of channel. Okay, one factor may be there, like the gate is placed. The gate means there are three terminals are there in case of MOSFET: source, drain, and gate. Okay, so there are three terminals: source, drain, and gate. So this gate terminal is placed above the channel. Okay, if you see the whole diagram, I will show the whole diagram. I will discuss in detail with the help of the diagram uh, in our classes, in detailed classes. Okay, after completing the quantum mechanics portion. So this gate is placed above the channel, and so there is a factor of capacitance, because the gate will be there. Then there are some dielectric material will be there. As we all know, silicon dioxide is the material which we use for as a dielectric material. And then there is channel, and as I told that depending on this channel, the MOSFET can be divided into two parts. So the channel are also two types. One is enhancement type MOSFET. That means we enhance the channel, we create the channel between source and drain and below the gate. Okay, not directly connected with the gate. In between that there is silicon dioxide layer, and then after there will be channel. It will be created. Initially there will be no channel, and then after we will create this channel. This kind of channel is called enhancement type. And then there is another type of channel which is depletion type. That means there is already a channel is there, and we just create a depletion layer, okay, inside this channel, so that we can control the flow of electron through the channel. Okay, so this kind of factors are there. But when we try to hello, I mean Okay, so okay, uh, there is a one student who will came here to sign the project report. For that reason, he called. Okay, depending on this channel, there are two types, and this channel are like this. Whatever I have told, that enhancement type and depletion type. And when we try to shrink down the size of the transistor and it's becoming nanoscale, then it's behave not properly, it's not behaving properly whatever we expecting. Okay, so this is called the scaling. There are certain limitations are there, so we need to understand the scaling limits also, that when we should stop and how we can manipulate the scaling of CMOS so that he can perform well. Okay, we need to discuss the FinFET also. Okay, vertical MOSFET we need to discuss, and that's it. In module 2, we need to discuss this kind of topics. Okay, related to scaling, related to FinFET, and scaling factor, limitations of scaling. Okay, this kind of things we need to discuss in module 2. So module 1 will be more of quantum mechanics. In module 2 we will enter to in electronics portion, and we will discuss in detail about the we'll discuss in detail about the uh, MOSFET, sorry, uh, after discussing the quantum mechanics, we need to discuss the MOSFET scaling. Okay, so that we can eliminate the scaling factors. Then we need to discuss the FinFET, which is the modern version of FET, that is field effect transistor. And then we need to discuss the vertical MOSFET also. Okay, in module 2. And then in module 3, we need to discuss about some basic portions of tunneling effects. You all know what is tunneling. We have studied in tunnel diode. So we'll again discuss with that thing, that is the tunneling. What is tunneling? What is tunnel diode? All these things are very important to understand in nanoelectronics. So we'll discuss that thing. Then quantum dots, quantum brackets, single electron transistor, which are the booming thing in today's world. We need to understand the single electron transistor. And if so, what is the importance of single electron transistor? As I have told that there are so many booming topics are there, but single electron transistor is one of them, because it can consume a very less amount of power. If we can develop this kind of transistor and we can use in practical applications as mobile and laptop, then the performance of this mobile and laptop will become very high. Very, we cannot think about that. A task which is performed by this kind of laptop or mobile with a whole day, if we implement the single electron transistors, then the whole task can be done with 1 hour. So you can easily understand that how fast it is. And why it is fast? Because a single electron will be in picture. Okay, basically in electronics we made the gates. Gate means a switch. Electronics, in electronics, whatever device we are developing, all these devices are basically switches. Like MOSFET is a switch. Sometime it will pass the current, sometime it will block the current. Okay, so it is basically a switch. So if we can develop a single electron transistor, then what happened? We can switch on or switch off that particular device with a single electron. Nowadays we are using thousands of lakhs of electrons which are flowing through the channel. But if a single electron can pass through the channel, we can understand that how much power we can need it. a very nominal amount of power we will need for this single electron transistors. And as there will be a single electron, so uh, so what happened? Power consumption will be very less. Channel will be very the flow of electron will be very smooth because of traffic. If we consider a road and thousands of cars are passing through that road, then there will be a traffic jam. But if there is a road and a single car is moving from here to there to transmit some data, transmit some operations or whatever it is, then obviously the efficiency of that transportation will become very high. As a single car is moving through that road, the single electron transistor is the same concept. Like if we can work or switch on the device or switch off the device with this particular electron, a single electron, then obviously the whole performance of the device will increase, and the power consumptions will also be very very low. Very very means very low. The power consumption is very low, and computational power will also increase very high. We cannot imagine that one. Okay, if you can develop successfully with this single electron transistor, computing power will be 100 times better than today's world, and power consumption will be 100 times less than today's world. So you can understand what is the importance of the single electron transistor. Okay, we will also discuss that topic. Then then we will discuss the carbon nanotube. Okay, so carbon nanotube is another very important, very trading topic. Okay, because carbon nanotube was a very small tubes are there. Okay, and as I was discussing about the channel of MOSFET, so here in carbon nanotube, what happened? We use a carbon nanotube. There is a tube, there is a pipe of carbon which is in nanoscale, and inside this carbon nanotube a single electron can pass, the same as the previous concept. So with a carbon nanotube, a single electron can pass through the carbon nanotube, and this carbon nanotube is placed in place of channel. Okay, why we are doing all these kind of things? Because we are trying to shrink down the size of the channel, and when we are trying to shrink down the size of the channel, there are some factors are there, like scaling factors. So uh, carbon nanotube can be one option to replace the channel, and one if we can implement this carbon nanotube in place of channel, then the overall efficiency will be increased. Okay, so this thing we need to discuss, and then we will discuss the applications of nanoelectronics or nanomaterial in medical applications. We'll try to do some simulations also to understand the concept. We'll also study the 2D semiconductor and electronic devices. Okay, in this module, and then we'll this is how we'll end up our curriculum for nanoelectronics. Okay, so this is the whole topic which we'll going to discuss in our curriculum. Okay, this is our introductory class where I have given the overall topics summarization in this lecture. So I'll stop the recording now, and I'll take some questions answer. And there is another important thing I need to discuss. Each and every day we will discuss few MCQ. Okay, we'll discuss few MCQ so that you can be prepared for your exam purpose from the beginning, and it will also help you to crack the exams for like GATE, NET, and job exams, whatever you will appear in near future. So we'll also discuss the MCQs also each and every day. Okay. So I'll stop the recording now, and we will discuss some few questions answered, and then we'll wrap it up.